we're looking at motion in one dimension. And the last few videos that we've looked at here, let me nudge this just a little bit on the screen. Okay, the last few videos that we looked at here, we've defined things that we need to know in order to understand, describe motion, and measure it. We know position in a fixed frame of reference with a set location to be 0 and a set of directions. We need time with a moment in time considered to be 0. We can then look at the change in position and call that displacement. We can then look at the rate at which position changes with respect to time and see that on a graph that becomes the slope of a position versus time curve. And if we're looking at the average velocity, that's just displacement divided by change in time. The displacement divided by the time it takes to do that change in position. We also found in the previous video that when we look at the area underneath a velocity versus time curve, that area is equal to the displacement that happened during that time period. So let's look at velocity versus time again. So let's say we have a velocity versus time curve, and we're changing velocity. And well, it too has a slope on that. And so we can look at the rate at which velocity changes with respect to time. We give that a name. We say that acceleration is the rate of change of velocity with respect to time. And for that, we use symbol A. And so it's also the slope of a curve. It's the slope of a velocity versus time curve. And we then could also say, well, we've got to be playing the same tricks here. We must also mean that that A average has to equal the change in velocity with respect to the change in time. And that change in velocity is going to equal the area under an acceleration versus time curve. So we have a couple different rates we're looking at here. Rate of change of position with respect to time, which is velocity. Rate of change of velocity with respect to time, which is acceleration. There are more rates besides this. More rates even with just dealing with motion. We have the rate of change of acceleration with respect to time is called jerk. Rate of change of acceleration with respect to time. The rate of change of a jerk with respect to time is called snap. And some lovely folks on the internet about 25 years ago or so decided, well, that's just too cool. So clearly the rate of change of snap has to be crackle, and the rate of change of crackle has to be pop with respect to time, respectively. And I don't know if those have been taken up by the broader physics community, but physicists tend to have a decent sense of humor about these sorts of things, so they're probably reasonably official. Anyway, we had these things, and we want to know, well, how can we work with problems with this? What happens? How can we work with acceleration and velocity? What if we want to know how far something goes? Well, we can do that if we have relationships between acceleration and position and time. And here's how we can do that. So, let's go ahead and make a velocity versus time graph. Let's see. I need space for algebra, and I need space for the graph. So let's sacrifice some things here. Let's make you a little bigger. And we'll see where we go with the algebra. So let's say that we have constant acceleration, and therefore we have constant velocity versus time slope. And here we have our velocity versus time graph, and we know that the area underneath this is going to be the same as the distance traveled. So if we find the area, we have to find the displacement. So let's label some things. Let's call this velocity here v0. And let's call this velocity at the end here v final. And we'll call this overall time here our change in time. Okay, so first off, let's look at a couple things. In this instance, our velocity is starting at some positive value and it's steadily getting faster and faster, larger and larger. And so the if it wasn't getting faster and faster, then the distance it traveled would just be however much area was under this rectangle. I'll call that like A1. And that's just going to be our original speed times the change in time. All right, so our displacement gets to be the original speed times the change in time. And if this is all in one single direction, we can make that displacement and velocity, let's say. And then if we had, since we are speeding up, we've got all this other area here as well. And that's a triangle. Well, we know the area of triangles. The area of triangles is 1/2 the base, which is the change in time, times the height. And the height here is the difference between the final velocity and the original velocity. So this distance here is v final minus v0. I'm going to write that as delta v for short. So, if we knew the final velocity and the original velocity and the time, we could use all that to figure out the displacement. And we can do a little bit of algebra here with that. But before I do that, I'm going to stick this equation over here for later. Let's say we have constant acceleration. Let's see. We had delta x equals v0 delta t plus half v final minus v0 delta t. Now we can do some algebra on that to clean that up a little bit. Actually, let's do that over there for the now. So we go ahead and do that. And we say, all right, so that's v0 delta t plus 1/2 v final delta t minus 1/2 v0 delta t. Well, we have a full v0 delta t over here, and we have half of a v0 delta t over there. So that means we're going to be left with just 1/2 v0 times delta t. We also have 1/2 v final times delta t. So the 1/2s and the delta t's are all being shared there. So we got v0 plus v final there. And I'll clean up the writing on this once we have a chance to take a look. So we've solved that and said that the displacement, if we know v original and v final and delta t, is this combination. It's half the starting speed plus half the final speed times the change in time if acceleration is constant. So I will stick that over here. Okay. So now what? Well, we also have this relationship here with average velocity. Average velocity told us that, or with average acceleration, rather. Average acceleration is change in velocity over change in time. And if this was constant acceleration, then the instantaneous acceleration and the average would be the same thing. So we know that this equation is also true for constant acceleration. I'm going to do a little bit of algebra there and say delta v equals a times delta t. We multiply both sides by delta t. And I'll stick that up here too. more space. Well, we want to know how far something goes when it accelerates, and we want to be able to know that if we know the acceleration, then maybe we could take this and substitute that in here. And so we get delta x is v0 delta t, how far we traveled if we didn't accelerate, plus 1/2 a times delta t times delta t again. That is v0 delta t plus 1/2 a delta t squared. Okay, so now we can talk about how far a thing moves when it's being accelerated if we model that acceleration as if it's constant acceleration. And so the good thing to do next is to see, well, when do we get constant acceleration and how does problem solving work with those situations? And that'll wait for another video.